Hi everyone, in this video we are going to discuss uniqueness of Taylor series expansion. So let us try to understand the statement first and then we will discuss its proof. So we have this power series summation n z minus z naught raised to n. It has some disk of convergence z minus z naught is equal to r. That means a circle we have with center z naught and radius r. It is a disk of convergence. That means if you take any point inside the disk, then for that point the series is convergent, and if you take any point outside the disk, then for that point the series is divergent. The given information is that power series converges to some function f of z. See, converges to f of z for each point of that disk of convergence, right? This is the given information, and we have to prove that series, that power series is nothing but Taylor series expansion of f of z. What we have to prove? We have to prove that power series is nothing but Taylor series expansion of the same function f of z. Okay, we are going to prove that thing. At the beginning, I am going to do a small construction. That construction is, I am going to consider a simple closed curve C. Let me draw in this diagram. I am considering a simple that means which does not intersect itself. So simple closed starting and ending point same, get it, around z0, and it entirely lies inside the disk of convergence. So such curve I have considered. Okay, so let us start with the given information. What is the given information? That power series converges to f of z. This is a given thing, so therefore I can write, let me write, we have that series converges to f of z. So simply we can write f of z is equal to summation n running from 0 to infinity an z minus z naught raised to n, right? It converges to f of z, so that's why both of them are equal for each point inside the disk of convergence, right? For adjustment, I am going to replace n by m. Both are variables, so we can easily replace n by m. Replacing, let me write n by m. Okay, so then what will we have? We will have f of z is equal to summation m running from 0 to infinity am z minus z naught raised to m, right? Yes, so this series we got. Let us continue it here. After that, I am going to consider one function. We will call it as g of z. So let me write, let I am going to consider a function g of z which is defined in this way, 1 upon 2 pi I into 1 upon z minus z naught raised to n plus 1. Okay, so here we have taken power n plus 1. So to avoid the confusion, n is there and this variable is different. So that's why I replace n by m. So now the variables are different. Here we have m and there we have n. So this function I have considered g. Clearly it is continuous on C. Let me mention clearly g is continuous on C. The function g is continuous on C because, tell me when this function won't be continuous, if the denominator is 0, and when we will have denominator 0 if z and z naught are equal, but it will not be possible because z naught lies inside the circle of that C, getting, z naught is inside this closed curve C and z is on boundary of C. That's why both of them cannot be equal, getting. So that's why clearly it is continuous on C. So all conditions we have. So in previous video we have already proved one result, that is term by term integration. So that thing I can use here. So let me mention, see, we want some space. Let us remove this diagram. Okay, so let me write here, therefore by term integration, getting. So see, this result we have already proved in our previous video. So if you want, you can watch that video. Okay, so that result says integration over C g of z f of z dz. Okay, so what does this result say? F of z means what? This summation. That means actually what we have, this summation inside the integration. F of z means what? This series, getting this summation, infinite summation inside this integration. So that result says we can interchange them. We can take summation outside, we can take integration inside. So that's why I can write summation. I'm putting the value of f of z, this value, but this summation I will take outside. So here I will have m running from 0 to infinity. So now, right now we have considered m, no? So m running from 0 to infinity. M is a constant, it will also come outside. We have integration over c, g of z. Okay, we don't have space, let me write here, into that z minus z naught will be there, z minus z naught raised to m dz. So by term integration, I got this one. Okay, so this is so much important thing. Let me call it as star. So now what will I do? We will find the value of left hand side separately. We will find the value of right hand side separately, and we will put those values in equation star. Okay, so I'm going to do that. Just make a screenshot of it, then I will go further. So let us continue. So some important part I have purposely kept here, so you can watch it whenever it is required getting. So let us go further. So let us start to work on left hand side. What is our left hand side? Integration over c, g of z, f of z dz. So value of g of z already we have. So let us put this value in this integration. So integration over c, 1 upon 2 pi I, 1 upon z minus z naught raised to n plus 1 f of z dz, right? So 1 upon 2 pi is a constant, so we can take outside the integration. So let us take it outside, 1 upon 2 pi I, integration over c, f of z upon z minus z naught raised to n plus 1 dz. Here also we have z naught. Okay. See, we can use corollary of Cauchy's integral formula. So let me write here integration over c, f of z upon z minus z naught raised to n plus 1 dz. So that corollary of Cauchy's integral formula, or you can also say extension of Cauchy's integral formula, says its value is 2 pi I upon n factorial nth derivative of f at z naught. So the same situation or the same integration we have got here. So let us use corollary of Cauchy's integral formula. So this is equal to 1 upon 2 pi I into the value of this integration is 2 pi I upon n factorial nth derivative of f at z naught. So let me mention by corollary of Cauchy's integral formula. Okay, by corollary of Cauchy's integral formula. So what will happen that 2 pi I and 1 upon 2 pi I will get cancelled to each other, and finally we will have nth derivative of f at z naught upon n factorial. So this is value of left hand side. So we found out the value of left hand side. So let us start to work on right hand side now. Okay, so make a screenshot of it, then we will go further. So let us start to work on right hand side now. Okay, so let me mention right hand side. What is the right hand side? We have summation m running from 0 to infinity, right? Am. We have an integration here over c, g of z, z minus z naught raised to m. Okay, this thing we have, and dz. So for simplicity, I will call it as Im. Okay, so let us denote it by Im. So let me write here. So this is equal to summation m running from 0 to infinity Am Im. Okay, so let me call it as equation number 1. So what will I do? I will find the value of Im separately. I will put the value of Im in equation number 1. So we will get the value of right hand side. Okay, but see, for finding the value of Im, we need to discuss 3 different cases. Actually, we have 2 variables, n and m. So there will be 3 possibilities. Either n is greater than m, or n is equal to m, or n is less than m. So let us discuss all these 3 cases one by one. So for the first case, n is less than m. Let us see what will happen. Im. What is my m? Im is nothing but that integration over c, g of z, z minus z naught raised to m dz, right? So what is value of g of z? Let us put it here. I am going to put the value of g of z here. So yes, so let me write 1 upon 2 pi I. It's constant, no? So I have taken it outside the integration, and 1 upon z minus z naught raised to n plus 1 into z minus z naught raised to m dz. So this is equal to 1 upon 2 pi I. See, what we have, n is less than m. This n is less than this m. That means the power of denominator is less than or equal to power of numerator. So we can shift this bracket to the numerator, right? Since its power is less than power of numerator, right? So if you shift it to the numerator, the sign will get changed. Power will be minus n minus 1. So let me write directly, this is z minus z naught m minus n minus 1 dz. Since I have shifted this bracket to the numerator, so sign became changed, and see, the base is same, so we can write in this way also, right? But see, now the denominator is 1, so that means there are no chances that denominator will be 0. So definitely it is a analytic function. So we know that if the function is completely analytic, then we can go for Cauchy's theorem. And Cauchy's theorem says the value of this integration is 0. So this is equal to 1 upon 2 pi I into 0. Reason is by Cauchy's theorem. Okay, by Cauchy's theorem. So let me repeat the reason. Okay, since now the denominator is 1, nothing is there, that means obviously 1 is there, right? Denominator is 1, and we have this polynomial function which is obviously analytic. And if the function is completely analytic, we can go for Cauchy's theorem, and Cauchy's theorem says the value of such integration. So let me mention here, what is Cauchy's theorem? Integration over c f of z dz. If the function is analytic, the value is 0. So simply I put 0 here, and 0 into anything 0. So the most important thing we have got, that means if n is less than m, so we got the value of im is 0. Let us go for the second case. Obviously second case is n is equal to m. Okay, so let us go for that. Just make a screenshot of it. So let us discuss this case, n is equal to m. Let us see what will happen. I am finding the value of that im, which is integration over c g of z minus z naught raised to m dz. So this is equal to, the value of g of z is this one. Let us put it here. 1 upon 2 pi I is a constant. You can take it outside. Integration over c, that 1 upon z minus z naught. What we have? N plus 1. But see, n is equal to m, so we can write m plus 1 z minus z naught. Okay, so g of z I have put here. So this is bracket we have. So let's write. See, z minus z naught raised to m and z minus z naught raised to m plus 1. So the bracket raised to m will get cancelled. And what will we have? 1 upon 2 pi I integration over c. Only one bracket will be remaining in denominator, right? One bracket is remaining in denominator. Since bracket raised to m will get cancelled. See, then we can go for Cauchy's integral formula. Okay, so let me mention what is Cauchy's integral formula. That formula is integration over c f of z upon z minus z naught dz is equal to 2 pi I f of z naught, right? F of, let me write properly. So what is f of z? 1. The condition is that function must be analytic. So 1 is a constant function, so obviously it is analytic. So I am going to use that Cauchy's integral formula. So this is 1 upon 2 pi I. Let us use it. Its value is 2 pi I. F means a function 1, numerator 1. So f of z naught, that means simply we will have 1. So let me mention the reason. By Cauchy's integral formula. Okay, by Cauchy's integral formula. 2 pi will get cancelled and we will have the value 1. So the second important thing we have got, if n and m are equal, the value of integration is 1. Okay, so let us go for the last case, that is n is greater than m. Okay, make a screenshot of it, then we will go further. So the last case is n is greater than m. Okay, I have written here. So we have to find a value of this im. So value of g of z is this one. So let us put here 1 upon 2 pi I is a constant, will come outside. integration over c, so that 1 upon z minus z naught raised to what? N plus 1. We have z minus z naught raised to m. Let me write 1 upon 2 pi I integration over c. So what will happen? N is greater than m. The power of denominator is greater than the power of numerator. See, bracket are same, getting? So power of denominator is greater than power of numerator. So let us shift this bracket to the denominator. Power will be negative, that means we will have minus m. So that's why we will have z minus z naught raised to n minus m plus 1 dz. Okay, so in that case, if you have the power z minus z naught raised to some higher power, then we should go for corollary of Cauchy's integral formula, which is integration over c. Let me write f of z upon z minus z naught raised to n plus 1 is equal to 2 pi I upon n factorial nth derivative of f at z naught. So this is corollary, or you can say the extension of Cauchy's integral formula. Let us use what is f of z? 1, which is clearly analytic function. This bracket has power sum n minus m plus 1. Let us do that. So 1 upon 2 pi I, yes, using this one, 2 pi I upon n factorial. So power is n minus m plus 1. So we will have n minus m factorial. Okay. After that, nth derivative, we have to take the derivative, getting? But we have a constant function 1. So if you take its derivative, obviously it is 0. So independent on z naught, getting, we will have the value 0, and 0 into anything 0. So in last case also we got the value 0. In first case, where n is less than m, we got 0. Third case, when n is greater than m, value 0. And of second case, where n is equal to m, we got the value 1. So let me mention that thing clearly, and then we will go back to equation number 1. Okay, so make a screenshot of it, then we will go further. So let us mention clearly the Im is equal to 0 if n is not equal to m, and it is equal to 1 if n is equal to m. Okay, so then 1 becomes, so let me write, right hand side is equal to, so we have that summation, so let us expand it. Okay, so m is equal to 0, we should start with 0, a0 I0, a1 I1, a2 I2, getting, plus and so on. In this way we will go, and we will go up to an minus 1 in minus 1, an in, an plus 1 in plus 1, plus and so on. Infinite terms are there, so I should write dot dot dot, right? So this result says, or this conclusion says, if n is not equal to m, the value 0. That means I0 0, I1 0, I2 0, all are 0 except in, which is 1. So that's why here we will get 0, 0, 0 everywhere except this in is 1. So an into 1, and remaining are 0 again. So obviously its value is an. So we have already calculated the value of left hand side, and we have got the value of right hand side. So let us combine. So let us put those values in star. Okay. So just make a screenshot of it, then I will go further. So therefore let me mention, therefore then star becomes, getting, so the left hand side we have got its value nth derivative of f at z naught upon n factorial, and the right hand side we solved, getting, right hand side, and its value is n. So let me mention here an. Then, okay, then, so initially we have already mentioned the series of f of z is summation n running from 0 to infinity an z minus z naught raised to n. So this is, they have already mentioned this power series is convergent and converges to f of z. So we have got this one. But right now though we have the value of n. Let us put this value of n in this series. Then we will have, this is summation n running from 0 to infinity. The value of n is nth derivative of f at z naught upon n factorial z minus z naught raised to n. So this is nothing but Taylor series. This is nothing but Taylor series of f of z at z is equal to 0. This is Taylor series of f of z at z is equal to z naught, right? This is Taylor series of f of z as z is equal to z naught. So in this way we proved if you have any power series which converges to f of z, then that power series is nothing but Taylor expansion of f of z at z naught, right? So let me mention hence the theorem as the theorem. So in this way we proved if you have any power series which converges to f of z, then that power series is nothing but Taylor series of f. Okay, so proof is over. Make a screenshot of it, then we will stop. Thank you. See you.